Swayam Prabha. Digital India. Educated India.
Now, one more important thing is Jahn-Teller theorem, right? What is Jahn-Teller theorem? It is there in front of you. For any nonlinear molecular system in a degenerate electronic state, a distortion will occur so as to lower the symmetry and remove the degeneracy. Does this remind you of anything? Anything we discussed in class in recent past? Okay, proceed. Now, the word symmetry is there, the word degeneracy is there. Yeah, what is that? What is that called? Configuration interaction also does the same thing, right? When you have two orbitals of same symmetry coming very close together in energy, they interact and they make sure that degeneracy is removed. So that is what I am reminded of when I read Jahn-Teller theorem. Okay, fine. So think of this. Is this a degenerate electronic state or not? What about this? Degenerate? So the point is, non-degenerate systems are these D3, D5 high spin, D6 low spin, etc., etc. Doubly degenerate states show more pronounced Jahn-Teller distortions. Triply degenerate states produce less pronounced Jahn-Teller distortion. Okay. Why are we discussing all this in a class of symmetry? If in D3 you have 3 electrons in 3 orbitals, right? So all 3 orbitals that are there are occupied, there is no other choice. Here you have a choice, here for example D2, you have the choice of having this or this or this unoccupied. Okay? In D3 there is no such choice. Okay. Fine. Why are we discussing all this in a class of symmetry all of a sudden? Distortion, symmetry will change. Can we have a complete sentence as an answer? That will be nice. So first was a word, second attempt was a phrase. Let's have a sentence now. You are right, tell me, just tell me what the answer is.
Point group will change, then property will.
Exactly. Due to distortion, what will happen is octahedral point group will not remain an octahedral point group anymore. What kind of distortion is brought about by Jahn-Teller effect? What is that called? Tetragonal distortion. It's called a tetragonal distortion. Tetragonal distortion. So generally what happens is, it is axial distortion, it becomes longer or becomes shorter. Okay. So let us talk about that. So this is OH for you, this is T2G, this is EG. Which orbitals are there in T2G? dxy, dyz, dzx. Which orbitals are there in the EG set? dx square minus y square and d 2z square minus x square minus y square orbital. Okay. Now when I have a tetragonal distortion, when axial ligands move out, then from octahedral point group I go to D4H point group, right? What will happen to these states? To answer that, of course, you will need the character table. What you need to know is what will EG break up into and what will T2G break up into if it does. D4H. Does anybody have the character table? Can you do that correlation? What is the, you know what I am talking about, right? I am talking about group subgroup relationship that we have talked about earlier. Okay, I am talking about group subgroup relationship between the OH group and the D4H group. And I am asking you, what is the fate of the EG group in D4H? Is there an EG point group in D4H? No. How many, why am I saying point group again and again? EG symmetry species. Do we have EG in D4H? We do? But does EG map to EG? Actually it doesn't. You work it out yourself, please. So this is homework. Correlation diagram between OH and D4H. Please work this out yourself. So if you use the character tables, it's not very difficult for you to show what I am going to show you now. What happens is that EG splits into two sets, T2G also splits into two sets, and using the group subgroup relationship, you can work out that the topmost level is B1G and that is dx square minus y square. Then you have A1G dz square, then you have B2G dxy, lowest energy is EG dxz dyz. So T2G breaks up into B2G and EG, whereas EG breaks up into B1G and A1G. Alright. So I think you have already studied Jahn-Teller effect, most of you. So what we are showing here is that how this Jahn-Teller effect, how we can predict at least some things by using a character table. If you know that you are going from OH point group to D4H point group, then you can tell, just looking at the character table and just by constructing the correlation diagram between OH and D4H, you can tell that what is EG in OH has to break up into A1G and B1G, and what is T2G in OH has to break up into EG and B2G. The question is, how will you say whether B2G is higher in energy or EG is higher in energy? How will you say whether B1G is higher in energy or A1G is higher in energy? How will you do that? How will you do that? Can you do it using character table, using symmetry? Can you do it? Can you say that it is necessary that A1G has to have a lower energy than B1G? No. So for that you have to go back to the diagram I was drawing, right, and you have to see that in D4H now, which are the orbitals that are affected more, which are the orbitals that are affected less. Okay. What is tetragonal distortion? I said axial ligands are moving out. Okay. So now you see in EG you have x square minus y square and you have dz square. So what I am saying is the ligands are moving out along z direction. So which orbital will get relatively stabilized? Dz square or dx square minus y square? Definitely dz square, right? So the energy ordering comes from there, but the fact that it is going to split, that can be predicted from symmetry itself. But using only symmetry you cannot say which one will be higher. Okay. Similarly, if you look at the T2G set, dxz and dyz have a z component, whereas xy does not have any z component. So when the ligands move out along the z direction, these are the orbitals that will be relatively stabilized. Okay. That comes from an energy discussion. Fine. So I want you to figure out what happens when you compress along z axis. What happens? Tell me. So will these two just interchange or not? Fine. And the other thing you work out yourself, square planar complex. work out the energetics and symmetry of the orbitals in a square planar complex. Okay. Now we move on to molecular orbital theory. We do not want to spend too much time on crystal field theory, and in molecular orbital theory actually our job is already half done. Okay. What did we say was our approach in molecular orbital theory? We said that we are going to work with, by and large, a system where you have a central atom and you have pendant atoms. Using the orbitals of pendant atoms, we are going to generate the SALCs. And then we are going to look for atomic orbitals on central atom that have the right geometry, right symmetry to combine with the SALCs. Isn't that what we said? Step 1, focus on the pendant atoms, get hold of the atomic orbitals of the pendant atoms that will participate in the bonding, generate SALCs, we will write. Number 1 is identify suitable atomic orbitals on pendant atoms. Number 2, generate the SALCs with these atoms. Number 3, identify AOs on the central atom that have matching symmetry with the SALCs. This is our approach, right? So that's what we have to do. And if you remember, for an octahedral complex, we have already generated the SALCs, haven't we? The sigma SALCs we have already generated. Fine. So all we have to do is we have to look at the metal atomic orbitals and find which ones of them have matching symmetry. That's all. So we start with ML6 octahedral complex, and to start with we say that we'll talk only about sigma bonds. But before that I want to ask you a question. In crystal field theory, excuse me, what is 10 dq? 10 dq. 10 dq? The difference in energies between Eg and T2g orbitals. Okay? So splitting. So this is how we do it in CFT. These are your d orbitals, right? Under crystal field, they are going to split, 2 at the top, 3 at the bottom. Diagram not drawn to scale, definitely, because it looks very symmetric. Pardon me for that, I am teaching symmetry after all. This energy gap is called 10 dq, isn't it? How do I write 10 dq? Capital D small q or small d capital Q? This is called 10 dq, right? Remember that. So 10 dq is the energy difference between the T2g set and the EG set, right? And all these orbitals come from the metal ion. That is what CFT says. Let us see what MOT says. Now, we have already worked this out. So, if you turn the pages of your notebook, you will find that the sigma SLCs that we generated for the pendant atoms breaks down into A1G plus EG plus T1U, right. Now, let us look at the atomic orbitals of the central metal ion. What do we have? See, 3p and all do not participate in this kind of bonding, let us leave them out. Okay. Let us focus on 3d, 4s and 4p. Whether or not there is any involvement of 4p, we will see very soon. Okay. So, here you see 3d orbitals, we know already that they consist of the EG and the T2g sets. Okay. 4s orbital, I think everybody will agree with me, is totally symmetric, A1G. What about 4p orbitals? P orbitals, I think we worked out for something or the other. P orbitals all transform together, right? They belong to a three-dimensional symmetry species. I was going to say a point group again, so I checked in the last minute. Three-dimensional symmetry species, and of course P orbitals are all Ungerede, right? Antisymmetric with respect to inversion. So the P orbitals, 4p orbitals belong to the T1U set. Shubhangi, okay with this? Achal, everybody okay with this? Now what do we have to do? We have to play matchmaker. Orbitals of same symmetry are going to combine with each other, and when they combine, they are going to give me a set of low energy orbital and set of high energy orbital, bonding and anti-bonding if you want to call them that. Okay. Now see, what do we have? We have sigma 1g, EG and T1U, right. Let us take sigma 1g first. Why am I saying sigma 1g? A1G, EG and T1U. Do you have A1G orbital here? 4s. So see, the A1G LCAO is going to combine with 4s. Do you remember what the A1G LCAO is? A1G is very easy, even I can write it. Right? Right or wrong? Sigma 1 plus sigma 2 plus sigma 3 plus sigma 4 plus sigma 5 plus sigma 6. What is the normalization constant? Root 6 or root 3? Okay, very good. Now, even without drawing that diagram, if I draw 4s here, does it not become apparent that 4s has the right kind of symmetry to form bonding and non-bonding kind of combinations with the LCAOs formed by this A1G set, right. So, if it is bonding, then this is plus, these are all plus, and the other combination is minus, this is plus, everything else is minus, isn't it, right. So, what have I done? I have just drawn the MO. I have drawn the bonding MO as well as the anti-bonding MO, right. I just have to change the sign. Okay. So, I hope you do not mind if I say that the A1G LCAOs are going to combine with 4s orbital, right. One low energy A1G MO and one high energy A1G star MO will be formed. Agree? How many nodes are there in this A1G star MO? One or six? One. We are spherical, right? So, it is a spherical node. Okay. What next? EG. Okay. Is there anything like Eg? 3d orbital. 3d orbital Eg is going to combine with Eg of sigma SLC. But oops, unfortunately for some reason I did have worked out T1u first, so please amuse me and let us work with T1u. So T1u, this T1u SLC that is there is going to combine with T1u orbital of the central metal ion, right. So this T1u and T1u star MOs will be formed. All right. Then now perhaps we can talk about Eg. I was thinking that there is some garbad in the order. This is what it is. I don't know why I animated it like this. Okay. Finally, Eg is going to combine with Eg, isn't it? So you get one Eg bonding, one Eg star anti-bonding. Ordering of energies can only be done if you do the quantum chemical calculation. Here we are only talking about the symmetries. Okay. What is left? Is anything left on the SLC side? Have you used up all the SLCs? All SLCs are used up. Is anything left on the metal ion side? T2G is left. So T2G remains as a non-bonding set. What is the meaning of non-bonding? T2G is localized completely on the metal ion, right? But look at this. What is 10 dq? This is 10 dq now. So this concept of 10 dq, this is 10 dq. The gap between T2G and Eg. The only difference between crystal field theory and molecular orbital theory at this stage is that you do have 10 dq, it is defined. Not the only difference, but the difference between CFT approach and MOT approach is that in CFT the T2G set as well as the Eg set all belonged exclusively to the metal ion. Here however, you see T2G is a non-bonding set of orbitals on the metal ion, fine, but Eg star, what is Eg star? It is an anti-bonding orbital, right. So it should have contributions from the metal ion as well as the ligands. Of course, you can say that it is very close to the metal ion in energy, the way we have drawn it, it is very close to the energies of metal ion orbitals, pretty far away from the SLC orbital. So the contribution of the metal ion is more, okay, but you cannot deny the fact that it is really an anti-bonding orbital. So this is the additional information that we get from MOT over VBT, over CFT rather. We get a bonding and anti-bonding character in the orbitals, and what we see is that this 10 dq that we get, that is going to be a transition from MOs, not MOs, non-bonding orbitals localized on the metal to anti-bonding orbitals that are delocalized over the metal and the ligands. So what kind of a transition will that be? The transition is from an orbital that is localized on the metal ion to another orbital that is delocalized to some extent over metal as well as ligand. Yes, yes, cannot hear, louder. So it is kind of a metal to ligand charge transfer transition, right. It is not pure DD transition anymore, okay. And if you fill in the electrons, then what will happen? Yes, sir. For that you have to do a little more quantum mechanical calculation, okay. That we are assuming, we are only talking about the symmetry aspect here. How many electrons would there be in the sigma SLCs? So where will they go? 1, 2, 3, 4, 5, 6. 6 or 12, how many electrons will be there? 12, no? 12. So we are talking about these lone pairs, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So see, all the electrons, right, 12 electrons go here. So where do the electrons from the metal get filled in? T2G and EG. So what is that? There is an agreement with crystal field theory. In crystal field theory, where did the electrons or where did the 3D electrons of the metal go? They remained in 3D orbitals. It is just that the 3D orbitals got split into T2G and EG sets. T2G is lower in energy. So whatever, so suppose configuration is D2, then what will you have? You will have 2 electrons in the T2G set in CFT. In MOT also you have 2 electrons in T2G state, isn't it? Because these are all filled orbitals, right? If you have 6 SALCs, that means they have originated from 6 orbitals, 6 atomic orbitals on pendant atoms, and these 6 atomic orbitals are completely filled. If you go back to the classical picture of dative bond, coordinate bond, that involves what? A filled orbital, right? Both electrons come from the donor. These are the donors, so these are all doubly filled. So you have 6 here, here also we have 6 MOs. So 12 electrons go here. So whatever is the electron configuration of the metal, that gets reflected purely in T2G and EG. So that is an agreement between CFT and MOT. Alright. So what we see is that it's unraveling in the way that we want it to unravel, to be honest. There is a correspondence with crystal field theory. However, we are getting more information. We are developing a more generalized approach by using molecular orbital theory, right? That is a triumph of molecular orbital theory. So this is 10 DQ for you. And of course, okay, that's what I talked about already. In my excitement, I forgot to press the button. I didn't realize that I have animated it also. Okay, so you understand what I am saying? Right. Moving on. There is no reason why we should be happy only with sigma bond. This is highly possible, and it happens that you have pi bonds also. Okay, and this is something that we have not worked out. Self-study problem for you. If you cannot do it, come to me, we will do it together. Okay. We have generated the sigma MOs, right? Similarly, you can generate pi MOs as well. It is worked out in Cotton's book, right? Not MOs, sorry, pi SALCs. When you generate pi SALCs, you get T1G plus T2G plus T1U plus T2U. Okay. Now what will happen? Sigma bonds are formed already. You have generated the energy diagram for sigma bonds. What is the symmetry of the non-bonding orbitals that you have, T2G? Do you have T2G here? You do, right? So what will happen? Pi bonds will form involving these T2G orbitals of the metal and the T2G SALC, pi SALC. Hi. What question? It was what? Yeah, of course, yes. But not necessarily back donation, you can have regular pi bond also. Back donation would be there when you have empty orbitals, like it happens in carbonyl. In carbonyl complexes, you have antibonding orbitals that are empty, and that can accept electrons from the metal. That is back donation. Okay, but here what will happen? This T2G and this T2G, they are going to mix, and once again you are going to have splitting like this. This then is the complete energy diagram of a octahedral complex involving sigma bond as well as pi bond. Okay. Where is 10 DQ now? Oh, sorry. Okay, we have to leave. We have to write these also. T1G, T2U remain as like non-bonding SALCs, you can say. So this is 10 DQ. So see, there is a qualitative difference between the 10 DQ that you have in octahedral complexes with and without pi bonds. If there is no pi bond, then this energy, then the T2G orbital is a non-bonding orbital on the localized on the metal, Eg star is anti-bonding orbital which is spread. Whereas if you have pi bonding also, then the T2G that you have is no longer non-bonding. It is actually an anti-bonding orbital. Okay? And as expected, the energy should be a little smaller than what you would have in absence of pi bonding. Okay? This is what I would like you to do. Yes. What was that? Because 4p orbitals are already betrothed, or whatever that word is pronounced. They are already taken. They are committed. They are committed to sigma bonding. And sigma is stronger than pi. So there is no reason why it should come out of the stronger commitment for an uncertain weaker commitment that has suddenly come its way.